Swayam Prabha. Digital India. Educated India.
Alright guys, you had seen iterative version. This version where we used a loop to find something is called the iterative version. The iterative version, that is we are repeating something again and again. This version is what you call as iterative version. So we have seen the iterative version of finding the factorial in the previous programming screencast. I had told you to observe the solution if you could find some patterns. I hope you would have found some patterns. Using that pattern, we will solve the factorial problem here in yet another technique, that is what we call as recursion. So recursion is nothing but a technique in which the programming languages allow a function to call itself again. This may sound confusing at the beginning, but as you go, it will be really very easy. So see, as I had said, if you want to compute the factorial of 4, 1 into 2, the product is 2, okay? Then the next time when you approach 3, product till now is 2, 2 into 3, you compute, it is 6. The product till now is 6, 6 into 4 is 24. That is how you got the answer, right? And observe that when you need 4 factorial, you are making use of the value of 3 factorial, that is 1 into 2 into 3, the value 6 is being used to compute 4 factorial. When you need 3 factorial, you are using the value of 2 factorial. So there is a dependency between these values. So when you need a larger value, you are requiring a smaller value to compute the larger value. So there was some dependency. So the n factorial depended on n minus 1 factorial. This was the general pattern you could observe from the solutions. Mathematically also, there is yet another definition of this. Is one definition of n factorial is 1 into 2 into 3 up till n. Another definition of n factorial is n into n minus 1 factorial. So for n minus 1 factorial, what would you do? N into n minus 1 into n minus 2 factorial. So on. So ultimately, if you keep expanding, where will you stop? As I had said, 0 factorial is 1. So that is where we stop. If you hit 0, you will say, I have reached the end. So 1 is the answer here. So till now, whatever has been the multiplicants, multiply 1 to it. That is nothing but by multiplying 1, the answer won't change. So we have reached the answer. So 0 marks the end of this procedure here. That is, we are depending on a smaller value for a larger value computation. This process stops at the point 0, right? So that place where we stop is what we call as the base case or the anchor case. I would write it here probably. Base case. Maybe I'll use the green color because this appears. Okay. So this is a multi-line command basically. This appears in green color, it will be easier, I guess. Base case or the anchor case, we can call it. This is nothing but point where your recursion is nothing but your dependency on something of the same type. That is, factorial of n is a computation. It depends on factorial of n minus 1. How is that computed? The same way. Again you apply the same formula, n minus 1 into factorial of n minus 2. So you are basically doing the same thing, but every time you do it again, you are doing it on a smaller number. So than to multiply 1 into 2 into 3 up to 100, if you multiply up to 10, then use it to find 11. then use it to find 12. You're basically breaking it into smaller things and solving it. So when you do that particular process where the bigger thing was depending on something similar, smaller instance of it, a bigger value of n depended on the similar kind of thing, a smaller value, right? Similar. This factorial computation is similar. 3 factorial depended on 2 factorial. 2 is a smaller value compared to 3. So something like that. N depends on n minus 1. N minus 1 in turn depends on n minus 2. This chain of dependencies, how this is being dealt, this process is called as recursion. A function calling itself with a smaller instance is what you call as recursion. So if it keeps calling, at some point it has to stop calling. We have to say that, okay, we have hit the answer. We have arrived at the answer. We have to say that. This particular point is what you call as base case or the anchor case, point where the recursion stops. So this is what you call as the anchor case. So let me modify this functionality. This particular thingy is not being used here. This is the iterative version. Iterative version. Now let me start off with the recursive version. Recursive version here. As I had said that factorial of n can be represented as n into factorial of n minus 1. This is yet another way of defining the factorial function mathematically. So this particular way we are going to use here. So where will it start? Factorial of 0 is equal to 1. What if negative numbers occur? They won't occur because here we are taking care of it. If negative numbers have been given as an input, we don't even call the functionality. We are calling it only on 0 or greater than 0 only. So here we need not worry about handling negative numbers because in the actual calling part we had handled it, so we are not worrying here. Okay, so this thing we are going to say. So the first step in recursion is always putting the base case. Base case. Here base case was factorial of 0 is 1. So I should say if we have passed the number as n is equal to 0, I should return the product as such, right? So let me use this statement. It's a product is initially set to 1, right? So this is not needed actually. I can even remove this. I can directly say return 1. So I should return 1. So I had returned 1. That is factorial of 0 is 1. That is why if n is 0, I return 1. Else, what should I do? I should return n into n minus 1 factor. Sorry, n into n minus 1 factorial. So I should call it as factorial of n minus 1. Let me give you an illustration before we actually run the code. So if I call factorial of 3, let's suppose. Let's start with a smaller value so that it is easier. You can extend it for any value, even for factorial of 100 or anything you can extend. That's not an issue. Okay, so how it begins is, it will first check if n is 0. 3, it's not equal to 0, so it will come to the else part. It will see 3 into factorial of 2. So the value of factorial of 3 depends on the value of factorial of 2. A similar instance, but the value inside is smaller. Okay, so now this particular thing has to be called. Okay, so factorial of 2 gets called. So again, see, factorial of 2. So 2 is passed here. N is equal to 0. No, 2 is not equal to 0. So it comes here. It will say 2 into factorial of 1. Okay. So now factorial of 1 gets called. Okay. What is factorial of 1 gets called? So 1 is passed here. If 1 equal to 0, that's false. So come back to else. Return 1 into factorial of n minus 1. So it will compute 1 into factorial of 1 minus 1 is 0. Okay, so now factorial of 0. 0 is passed here. N equal to 0. 0 equal to 0. It's true. So it will return 1. So this will return 1. So now your calculation will go in the upward direction. Okay, let me show you the upward calculation. Okay. So 1 is returned. So it goes one level up. And so it will calculate 1 into 1. What is the answer? 1. So that particular value is passed to one level up. Okay. So 2 into what is the value being passed there? 1. So that is being calculated here. So as 2 into 1 is calculated here. 2 into 1. This 1 is the result passed from one level below. For it, the result is passed from one level below. So the computation breaks down into smaller numbers, and once you get a number where you know the answer, you trace back till you get the larger answer. That is how we are working here. Okay, so 2 into 1 is 2. Okay, let me now say. So 2 has been passed here. Already it was having 3. 3 into 2. So 3 into 2. Okay. What is the answer? 6. So this thing has called it. So it will get the answer as 6. So this answer will be passed on to the main function where you have called this. So when you call factorial of 3, it will keep splitting the problem into smaller ones until it knows the answer. And once you know the answer, trace in the backward direction till you get the answer for the larger problem. This is how recursion works. Okay, this is the working of recursion. Let us start a new console and let us run it. Okay. But before that, I have to save this. I will save. Okay, so let the console start. Okay, so it has started. Let me run the file. Okay, enter a positive number. The same negativity check. All these are the same, so I am not giving a negative number. Let me give back a positive number. Let me say 5. Factorial of 5 is 120. So in a similar fashion, it will break down. 5 will break down to 4. 4 will break down to 3. 3 to 2. 2 to 1. 1 to 0. For 0, you know the answer. Now use that answer. Trace in the backward direction and you will get the answer as 120. So this is how the recursive programs work. I hope you understand the concept here, or it's not a very difficult thing, it's an easier one. All that you need is some practice, that's it. Take some examples, you try thinking in this fashion, you try breaking into smaller pieces, then once you get the answer, try constructing back the actual answer. So I hope you have been remembering the movie clip that has been shown at the beginning of the video. The person would ask answer for something to a person before him, the thing keeps on propagating till someone who knows the answer. Once you get the answer, you propagate in the backward direction to the person who has asked the question. In this case, what is factorial of 3? That is the question asked by your main function. That is the question asked by your user. So you cannot compute it directly, so you try splitting it into a smaller instance. So that is something analogous to asking the person before him whether he knows. So whether this thing can be calculated, it checks. Even this cannot be calculated, so again split. If this can be calculated, no. So again split. Can this be calculated? Yes. So calculate, use the answer and propagate in the backward direction. I guess now you understand why we had shown the movie clip and also how the concept of recursion works. This is really a very powerful concept in computer science. It will make it intuitive things be easier to code. That is, some things will be intuitive for us. We will have in mind that this is how things has to be done. But how would you translate it into a code? It may be difficult if only iteration were for rescue. Recursion is handy in many situations. You would come across as you keep learning some advanced stuff. Even in some stuff what you had learned till now, you can have a recursive version for some problems. Please note that for this we had an iterative version as well as a recursive version. So for every recursive version there is an equivalent iterative version too. So you can use anything that is convenient for you, and in some places recursion is highly intuitive and easy on minds. So one such application we'll see in the next video. Thanks for watching. Have a nice day. Alright guys, hope you had learned about the powerful technique of recursion. I hope you remember search algorithm that you had studied previously in your previous weeks, namely the binary search. Let me give you a very quick overview of what it does. It is basically how we search for something in a dictionary or in a telephone directory, something like that. Why did I take dictionary or telephone directory? Because the words or the contents in the directory are sorted, or that is they are arranged in some ascending order, they are arranged in the alphabetical order. So that is why we can apply this technique. So binary search basically calls for a sorted list. You want a list that is arranged in some specific order, either ascending or descending. It calls for a list arranged in this order, and in that list you want to see whether a particular number is present in the list or not, or whether a particular item is present in the list or not. So what would you do? You would check the middle of the list. If that is your required item, you are done. Else you check if it is less than your required number or greater than your required number. Accordingly, you will branch on to the left half of the list or the right half of the list. So this is how your binary search works. You had seen the iterative version of binary search in your previous weeks, I guess. So that is easier, but still an easier thing. Like how I had given you an intuitive version of binary search, like you have to scan into the left half, you have to scan into the right half, something like that. I had given you an intuitive version. So such an intuitive thing can be easily translated into code when you use this technique of recursion. So let us see how we can use recursion to simplify the process of writing code for binary search. Let me say, I'll define binary search. Define binary search. For this, I need list, or I can call it list L. I need a list L, some element X which we want to find. You were processing it using the index values. You would have seen that till now, you may be familiar, but still I'm just giving you a very quick recap. Indexes in computers starts from 0. Humans start counting from 1, but computers start counting from 0. So the counting starts from 0. So if your list has 5 elements, the counting would be done as 0, 1, 2, 3, 4. 0th element, first element, second element, third element, fourth element. This is how your computer counts. So you have to give the starting index and the ending index. These are required for your binary search, right? So initially your starting index is 0, ending index is actual end of your list. So that is the entire list. Then as you scan the middle element, you keep discarding one half of the list and just keep searching in the other half. So that time it will change. So these are the things you need to do binary search. You need a list, you need the element X which you want to search, you need a start and end index of the list where you want to search. That is, you won't search the entire list all the time. You will search parts of list by discarding the unnecessary half. This is how your binary search works, right? So we needed these 4 parameters. Okay, let me define. As I had said, recursion requires base case. What is the base case? When we have only one element left in our list. If just one element is left in our list, then we have to see that particular element. If that is the required element, then you say yes, the element has been found, else you say the element is not found. Okay, so for element not found, I am going to return a value -1. I am going to assume that my list has all positive values and -1 is not the value in my list. Also, I am going to return the position of the element. I am not going to return the element. Even if you have negative elements, I don't mind, that's fine. I am going to return the binary search. Basically here I am going to return the position in which the element is present at the list. So that is what I am going to return. So position starts from 0, right? So if the element is not found, I will return -1. That is, the element is found somewhere outside the list. That's what basically I mean. So I'll return -1 in case if it is not found. So the base case is one element. Just one element in the list. That is the base case. So if there is just one element in the list, how would your start and end be? They would be equal. Start and end will be the same value because there is only one element, that is the start as well as that is the end. So I'll check it using the start and end indices. If start is equal to end, I would check if L of start or end, you can use anything interchangeably because they both are equal in this case. If that is equal to your required element X, you return the start value, that is, return that position. Else, there is just one element. Say suppose, assume you have just one element 10 in your list and what you want to search is 50. 50 is not present in the list and it is having only one element. Then you have to say element not found. For that, I said the code I am going to use, the encoding I am going to use is -1. So I'll return -1 there. Element 50 is present in the -1th position, meaning that it is not present. Okay. So I'll return -1 in that case. Okay, this is the base case. If the base case is not true, then else. That means there are more elements in the list. In that case, you have to find the middle element and you have to discard the unnecessary half and search through the required half. You have to split the array into halves and search through the required half. That is what you have to do, right? So divide the array into halves. This thing we have to do. For that, we need to find the mid position. Mid position is nothing but start plus end. So I have to put a bracket because I need to calculate the sum first, then I have to divide by 2. That is, it is the midpoint, right? This is intuitive. Start and so here will be your start and here will be your end. The midpoint will be start plus end by 2. This will be your midpoint. When you divide, there is a possibility that you can get some value that is a floating point value, maybe 7 by 2, 3.5. What is the meaning for position 3.5? Either you have to take it to 3 or to 4. So for that we are using a functionality int. So we are typecasting it to integer because position is a we want it in an integer. That is the first position, second position, third position. This is what we want. We don't want 3.5th position. So we'll use int. So it will have its own conversion. It will either take it to 3.5 to 3 or 4. Maybe we can run here and check. Int of 3.5. Let me give 3. So it is taking the floor functionality. Floor is nothing but the integer that is closest to it. That is the greatest value of the integer that is closest to it. If you take the number line, 3.5 is somewhere here, 3 is here and 4 is here. It is going to the left side. So int functionality is going to the left side and taking the greatest integer. 2, 1, everything is present in the left, but the greatest in the left, the integer is 3. So 3 is returned as the answer. So that will be taken here. Let me start a new console better because for this program we need a new console. Okay. So this is the midpoint we have computed. We have to check if the mid element is the required element. So if L of mid is equal to x, that is the case, we are done. We have found the element. Return the mid element. Else I have to check if it is greater or less. So I would say L of mid is greater than x. Means you have a sorted list and the middle element is greater than your required element. So where should you search? Definitely your element will not be in the right half. You can discard the right half and you need to search the left half. So your array would now shrink from the starting position to mid minus 1. So mid position didn't have the element. Also there is no chance that it will be after mid. So it will be before mid. So we need to shrink the array up till mid minus 1 position. It is 1 position before the mid. Up till that we need to shrink the array. So that is, we'll do it as return the result of binary search on the same list for the same element x. The start position is not changed. See, because we have to check the left half of the array. So the start position is the same, but the end position is not the previous end position. Previously we had a bigger list. We want to split it. So the end is mid minus 1. Why mid minus 1? Because at mid position we had checked. Mid position didn't contain the element x. So and x is a smaller value. That is x is L of mid is greater than x, meaning that x is less than L of mid. So x being less than the mid value will be present in the left half. So from starting position till 1 position before mid, whatever is the array left, search in that array and return the answer is what we mean. See, it is really very intuitive. See, this is the left half. This is the left half. Then using of iterative method, recursion is easy. You can translate your intuition into code very easily if you use the recursive ideology. Okay, so this is the recursive way to call the left half of the array. Call the procedure on the left half of the array. Search the left half. Else you have to search the right half. So for the right half, end value is the same, but the starting point is different, right? We had searched up till mid. We didn't find it at the position mid, and the value x is greater than the mid value. So it would be present from anywhere from 1 position after mid up till the actual end point, right? So your start value will change So I would say return binary search result on L, X, mid plus 1 and end. The modified starting point is mid plus 1. Till mid position we had checked there was no element, that is why we are checking the part after the midpoint. Here we are checking the part after the midpoint. Here we are checking the part before the midpoint, that is the left half and the right half. Whatever we had it intuitively in our mind, we are translating into code very easily. So this is the power of recursion. So it would recursively keep computing and you will get the answer. So you can take any example. I had given you an example of how recursion works in the factorial screencast. Similar to that, you take a list, you try applying binary search on it, you try how recursion works. You would have understood how recursion works. So this particular search, the bigger list, depends on the value of searching on the smaller list. So whatever the result you get after searching on smaller list will be translated back and will be returned as the result for searching on a bigger list. This is how your binary search works in the recursive manner. So we had defined binary search, now we have to use it, right? So let me give a random list. You can also change it with your version. You can ask the user to input how many numbers he want to input. You input that many number of numbers, or till he presses some key you keep getting inputs. You can by now I guess you all are familiar with the various conditional constructs. So using that you can modify the code as you wish. Now my motto is to demonstrate binary search, so I would just give a smaller list, 20, 45, 60, 70, 90. So this is my list I have given. Please note that I have given the list in the sorted order. If it is not sorted, you have to apply sorting first. Then after you get the sorted list, you have to pass the sorted list to the binary search. Binary search expects a sorted list. So that is very important. Please make a note of it. So this is my list and I will input the X value from the user. Okay. Let me input the value of X from the user and I have to typecast the inputs in my Mac machine. So I am typecasting. You please follow as per your machine's dependency. Input, enter, search key, I would say. But that is what number you want to search. I would input the search key from the user. That is my X. So binary search will return the index, right? So let me store it as index is equal to binary search on the list L, search key X. Starting position is always 0 for the bigger list. Initially we start with the entire list 0 and the end position is 0 to length minus 1. This is a 5 element list, so it will be 4. So let me generalize it. Let me say length of L. This will give the length of the list, that is how many elements are present in the list, will be returned by this length of the list minus 1. This is the ending index. So you initially start off your search with this particular index. This is the, suppose my search key is 80. This will be the entire list will be passed. So it would find the mid value 60. It is 80 is greater than 60. So this half is not needed. This is neglected and this particular thing will be executed. And 70, 90. This will be my new list. In this list, I will search for my key 70 and 90. This will be taken as a mid value, as we have seen. That floor value is taken. So this will be taken as mid value. 80 is still greater than 70. So it will skip to the right half. So here there is only one element 90. So this case would be executed. 90 is not equal to 80. So it will return minus 1. So I will come to know that this thing is not present. So something like that it works. You can trace through it. I hope you are now clear with how recursion works and you are clear with the binary search concept too. So you can understand it. All that you need is take a pen and paper and trace through how some examples work. That is what is required. With that, you can easily understand the concept. Okay, so it will return the index where the element is present in the list. Okay, so I have got the index. So if I just say the index, it is not enough for a normal user. For us, element 60 is present at the third position. If I say 2, they'll say what is this? The computer doesn't know even this. So we have to translate it into a human friendly format, right? So basically what is that we have to do? We have to add 1. 1 is represented as 0. The index in second position is index 1. Third position is index 2. So basically whatever is the index it returns, add 1 to it and display it to the user. And if it returns -1, you should not say it is present at index 0. You should say that the element is not found. You should print the appropriate message. So first we will give a check that if index is equal to -1. In that case, you should print x value not found. Okay, x value is not found. Okay, else you should print, that is -1 is not the case, then you should print that x value is found at position index +1. The computer's counting system and the human's counting system differ by 1. So that's why we are adding 1 and displaying. Okay. So this is how you have done. So let me save the code. I hope you are clear with it. We have a list. We input a search key. This you can even modify it to getting the input for the list elements from the user. You have to sort the list. Please note that you have to send a sorted list for binary search to occur. So you have to sort that list, input a search key, then you apply binary search on it. How it works? If there is just one element in the list, it will check if that element is the required element X. If it is the case, it will return the index, else it will return -1. So whenever the element is not found, it will return -1. That is how we have encoded it. In case if the list has more than one element, what it does is it will find the mid element, and based on the mid element, since the array is sorted, it will discard one of the halves. If the element required is exactly the mid element, we are done. If it is less than the mid element, you have to search the left half. So it will discard the right half. It will search only the left half. If it is greater, you have to search only the right half. It will discard the left half. So for this, to understand really well, I would suggest that you take a 20 element list basically and you try tracing it on a paper. Basically to understand this clearly, you should work out a lot on paper and less on computers. Computers can do this in fraction of a second, but for humans to understand this strategy, it requires some practice. So please take a pen and paper, take some 20 element list randomly, you sort it. Maybe for that you can use a computer as well, because sorting a 20 element list may take some time. So you can use a computer as well. You sort it, you take this, or you take a sorted list of 20 elements. You randomly give some search element. You give some element which is present in the list as well as some element which is not present in the list. Try to understand how the various runs of the programs are, and you will really understand the process very easily after practice. All that is needed is practice. Please do practice, practice, practice. That's it. Okay, now let us run this program. Let me run it. Okay, it is asking me to enter a search key. Let me enter 80. 80 not found. Perfect. Okay, now let me enter 90. Let me enter 90. 90 is found at position 5. Perfect. You got it? Maybe when I entered 80, 80 is not found in this list, so it says 80 not found. And when I enter 90, 90 is found here, it is found at position 5, so it says 90 is found at position 5. So it works. I would recommend that please you take some pen and paper and work through various examples, work through a list with large elements as well. Here just that I wanted to demonstrate the recursion technique, I had taken a smaller list, an already sorted list. You try different things, unsorted list, you sort it, then apply binary search, a huge list, a list where you get somewhere, if it is a 20 element list, try to find the 6th, 7th element, try to find the 18th element, try to find something exactly near middle or near the middle, something like that. You try various possibilities, you will understand actually what is the logic of binary search, how it works. You will understand. All that is needed is practice with pen and paper. Keep practicing. Thanks for watching. Have a nice day. Alright guys, hope you had seen a few examples of how recursion works. This is yet another mathematical function or mathematical sequence, I would say, which can be easily computed using recursion. So this is what we call as the Fibonacci sequence. Let me give you some explanations in comments before I start off with the coding. So we are going to see what is called the Fibonacci sequence. I guess you guys are familiar with it. Still, let me give you a very brief overview. So the Fibonacci sequence starts with 0 and 1. This is the 0th Fibonacci sequence. Same like computers, here the counting starts from 0. 0th Fibonacci sequence is 0th Fibonacci number is 0. Let me write one by one, that's better. 0th Fibonacci number is 0. Sorry, it's 0. Sorry, I'm sorry for this. 0th Fibonacci number is 0. The first Fibonacci number is 1. Second Fibonacci number is nothing but, now you have got two numbers. Let me put it, okay. So given that you got two numbers, you add these two numbers and you got the result as 0 plus 1 is 1. So this is your second Fibonacci number. The third Fibonacci number is nothing but, add the last two, 1 plus 1, 2. 2 is your answer. The fourth Fibonacci number is 1 plus 2, 3. 3 is your answer. The fifth Fibonacci number is 3 plus 2, 5. This is your answer. And so on. And it keeps going. It keeps on going. This is an infinite sequence basically. The initial two values are nothing but the seed values they had given. These are the, in our recursion terminology, this is the base case or the anchor case. This is the base case or the anchor case. For these two things, we know the value, we can directly return the value. We can directly say this is the value. If they say I want the first Fibonacci number, you can directly say first Fibonacci number is 1. If someone is asking you the 10th Fibonacci number, something like that, you don't know. You need to calculate it. So using 0 and 1, you find 2. Using 1 and 2, you find 3. Using 2 and 3, you find 4. So do you see? A bigger value of the Fibonacci number, that is the nth Fibonacci number, depends on the value of n minus 1th Fibonacci number plus n minus 2th Fibonacci number. So it depends on the previous two values, right? So here we can apply recursion and we can easily find the nth Fibonacci number. So our objective here is to find the nth Fibonacci number. Fibonacci number. We can have an iterative version of the code too, but in this case I would leave the iterative version of Fibonacci number as an exercise for you guys. Please do try it. It is not very easy. It requires some amount of thinking, but it's not Herculean task or something like. It's not rocket science. It is doable. So you need to invest some amount of time. You invest some amount of thinking. If you do that, you can find the iterative way how to find the Fibonacci numbers. So that I would leave it as an exercise. I would demonstrate the recursive way for you guys. Okay. So let us start off. I need to define Fibonacci. I would say Fibonacci of n. Nth Fibonacci number is what I want to find. I know the 0th Fibonacci number and first Fibonacci number. 0th number is 0. First number is 1. So in this case, I need to return, if the given n is 0, I need to return 0. If the given n is 1, I need to return 1. So if n is 0 or 1, I need to return back the n itself. So that is my base case. Okay. So that is why I had given a space here as well. This is the base case and maybe I'll put a dash here. This is the base case and these are derived from the base numbers. Okay. So this is the base case. So let me first put it if n is less than 2. And similar to that, for negative value of n, Fibonacci is not defined. We need to check that in the main part where we are calling this functionality. Same like factorial, how it is defined just for positive numbers and 0 and positive numbers. Fibonacci is also defined only from 0. For negative numbers, it is not defined. So let me say 0 and 1, right? So let me say if n is less than 2, just return back that n. If it is 0, return 0. If it is 1, return 1. So return back that n. Okay. Else, if it is greater than or equal to 2, from 2 onwards, we are dependent on the previous values. So you should return back the Fibonacci of n minus 1 plus Fibonacci of n minus 2. Maybe you want the second Fibonacci number, you should return Fibonacci of 2 minus 1, that is Fibonacci of 1 plus Fibonacci of 0. That is how we calculated. Fibonacci of 1 is 1, Fibonacci of 0 is 0. That is the first Fibonacci number is 1, 0th Fibonacci number is 0. So 0 plus 1, we got 1. That is how we had calculated, right? So that is what we are doing. You take the previous two Fibonacci numbers and add it, is what we are doing. If you need the third one, what you do is second plus first. First one you know the value, so substitute 1. Second Fibonacci number you don't know, so you calculate second Fibonacci number plus 1. For getting second Fibonacci number, again you call it. For second it is first plus 0th. So 0 plus 1 is 1. 1 plus 1 is 2. So you will get the third Fibonacci number. So you can trace it on a paper and you will understand the working. So this is how basically Fibonacci numbers work. If it is less than 2, just return back the same value. Otherwise, return back the sum of previous two values. Right? This is the intuitive way of explaining Fibonacci numbers. See, we have translated our intuition. We have translated the intuition into code very easily. All thanks to recursion. With this powerful technique, we can really make this code very, very easier. But for iterative version, you can write an iterative version. I don't say that with iteration it is totally impossible. You can write an iterative version, but it requires some amount of thinking to be invested here. Okay. So I have got the answer. So I should take an input. N is equal to an integer input is what I wanted. So I'll typecast because of my machine dependency. I'll typecast input. Enter a positive, maybe I can say a non-negative, that is better because 0 is also defined, right? So I should say non. Even in factorial, please make the correction there. It is non-negative because 0 factorial is 1 is also defined. So enter a non-negative number. Enter a non-negative number is the input, is the message I got, and some input I will get. Still I need to check in case the person has by mistake entered a negative number. I shouldn't throw at him some results that is incorrect. So I should throw him, I should tell him the suitable message properly. So I will print undefined for negative numbers. N is less than 0, meaning that it is a negative number. Whatever input he has given, what is undefined? Fibonacci numbers is undefined for negative numbers. Okay, so I will say Fibonacci numbers are undefined for negative numbers. Okay, so I had given it Fibonacci numbers are undefined for negative numbers. Else, if it is not a negative number, then I should print the nth Fibonacci. Nth is not correct because if he gives first, second, I have to put ST and D appropriately. So that formatting is needed. I would modify the message instead smartly. Fibonacci number at position, sorry, it is position, sorry for this, position n is, I should call Fibonacci of n. Alright, I hope you guys can understand this till now. See, I take a number, input, a non-negative number, 0 or positive, I agree. If it is a negative number, I say it is not, it is undefined. I print this message. Else, I call this functionality Fibonacci on n. Okay, so if I call this functionality Fibonacci on n, if that number is less than 2, for 0th Fibonacci number is 0, first Fibonacci number is 1. This is something defined as the base case for us. So in that case, I will return the value of n. Otherwise, I will compute the sum of previous two Fibonacci numbers, right? So this will input the nth Fibonacci number. So for first, let me verify. For that, let me enter 5. If I enter 5, I should get 5 as the answer, or maybe if I enter 4, I should get 3 as my answer. Let me verify it first, then maybe I will find the other Fibonacci numbers. Okay, let me run the file. Okay, enter a non-negative number. I will enter, so just for verification, I enter -7. Fibonacci numbers are undefined for negative numbers. Yeah, I got the proper message. Okay, now let me test it. If I enter 4, the fourth Fibonacci number is 3. I should get 3 as my answer. Let me run it. Enter a non-negative number. Let me enter 3. Sorry, 4. Fourth Fibonacci number is 3. Third Fibonacci number is 2. Fine, you can do it. Let me enter 4. Fibonacci number at position 4 is 3. Yeah, it is working. So now let me find out the 10th Fibonacci number. Let me do 10th Fibonacci number. Fibonacci number at position 10 is 55. Maybe you can list the numbers like this and you can verify. But it's correct. So once it's working here, definitely it will work for any value. So using this program, you can find the Fibonacci number at the nth position in the sequence. In the Fibonacci sequence, what is the number present at the nth position? So here nth is, luckily, this is one thing in mathematics which is very close to computer science. Counting starts from 0. So nth number is nothing but, for humans counting style, n plus 1th number. Please have that in mind. Here counting starts from 0. I would recommend that you guys invest some time thinking if you can do this in an iterative fashion. It requires some amount of thinking to make it iterative, but it is possible, it can be done, but it is not straightforward. It requires some amount of thinking. So when you invest some time for thinking in the iterative style, you would definitely appreciate the technique of recursion, because it lets you do something straight away from your intuition. Whatever you understand from someone's explanation, you can straight away translate it into a code. Recursion allows that thing. That particular thing is difficult when you do it in the iterative way. But still, it's not a rocket science, it's doable. Please do invest some amount of time. Try doing the iterative version. And please do discuss in the discussion forum of how you tried the iterative version, what are the challenges you faced, or if you can print the sequence, Fibonacci sequence, if they are asking the nth Fibonacci number, can you print the sequence starting from 0 up till the nth Fibonacci number? Can you try that variation? You can do a lot of things. Please do explore and keep trying more examples so that you understand how recursion actually works. Thanks for watching. Have a nice day.
As you all know, life is full of ups and downs, and so is our next game. Our next show is about snakes and ladders.
Six. That will be 1, 2, 3, 4, 5, and 6.
You will get another chance.
Oh, 6. Oh, okay, right. 1. That's a 1. 37. Okay, perfect. 4. 1, 2, 3, and 4. So, the game that we are playing is called the Snake and Ladders. The game again involves a whole lot of randomness, and there is no place for logic or thinking. So the idea is very simple. You start with 2 pawns. As you can see, I am red and she is blue. We start with 1, and this is a die where I roll, and then if it's 5, I start keeping 5. So let's say, for example, we both are here, and I roll this, it is 2, and I say 1, 2, and then she rolls. Can you roll, Bhavna? It's 3, and she puts 3. And whenever we encounter a ladder, we climb up, and whenever we encounter a snake bites, you see, we come down to its tail and then continue. You see, assuming I climb up like this and finally come here, just in case I put a 2 from here, the snake bites and I may have to come down to 23. So that's the rule of the game. The point is, anyone who reaches 100 wins the game. So Bhavna, where were we? I think I was, you were on 81, I was on 87. Okay, yeah, perfect. And I should now play. Maybe I'll play once more.
No. I think you were about to get bitten by snake, so let's go ahead.
No, but I was explaining the game. I think I should get a second choice.
No, I don't think in this game you will get.
Come on, I'm not a cheater cock. Okay, so let's continue from here. 1, 2. Okay, fine. I'll accept that it was 2. you saw the game. It has very simple rules. Anybody can follow it and start playing it immediately. So what you do is you roll a die and move your pawn accordingly. Assume you were on, let's say 15, number 15. You roll a die and you get a 5, which means your pawn moves 16, 17, 18, 19, 20. And 20, in case if it's a snake, you come down a few units. If it's a ladder, you climb up a few units. So this game is very popular all over the world. Although it originated in India, it is now very well known in different parts of the world, and there are variants for this game as well. So that aside, we will now see how we can write a piece of code to simulate this game, where two people can simply sit in front of their computer and then play. So a word of advice, since you people are beginning to code, you needn't worry so much about doing the exact simulation. Putting a board and displaying a snake and ladder may not be required. Let us do it with plain text. Let's see how this can be done.